Hey, we're continuing with section 5.3. We want to wrap up talking about the multiplication rule by specifically dealing with two things today. We want to really focus in on independence, as that's something we've been talking about. So I want to hone on the idea of independence. And then also, I want to talk about complements a little bit. So they kind of go hand in hand in some cases. All right? So two goals. I can determine if the events are independent, and also we can find the probability of something of at least one. So sometimes you're going to be asked that, and we can find a shorter way than to go crazy. So a couple things about independent. Two things that are independent, what that means is one doesn't affect the other. Like the occurrence of one does not affect the occurrence of the other. All right? Now, if they are dependent, then that would change it. Meaning, typically the old school way of figuring out if two things are independent, it's just using a formula for and, using a memorized formula, finding each of these three probabilities, and I know the second one doesn't apply to you guys because this was an in-class activity, but the probability of A and B, the probability of A, find the probability of B, and if this formula holds true, then they would be considered independent. However, if it doesn't, then that means that this one must be different because it's different based off of it being dependent on probability of A. So that is all good and fine, and that can work. The preferred method in AP statistics now is, we're going to call it the new school method, is to give some idea of what that actually means, like why it actually works. So start with the concept of independent events. A and B are independent if knowing whether or not one event has occurred does not change the probability of the other event happening. Okay? So let's consider both cases. This is talking about evil eyebrow and taco tongue. It's something you can do, whether or not they have anything to do with each other. So if one has occurred, let's see what the other one, what the probability of the other one has occurred. And let's see, just in general, what is the probability of one occurring. If those are all the same, then it doesn't change no matter what the circumstance is. It's going to be independent. But if one occurring, like in this case, changes the probability of taco tongue in this case, then it's not independent anymore. They would be considered dependent events. Same thing here. We're ultimately finding the probability of taco tongue for all of these. But if it's dependent on something else and changes, then it's no longer independent events. So if they're equal, we know they're independent. If they're not, well, they're not. This part is memorized. This part is the opposite of the memorized formula approach. And it is considered more appropriate because it gives you the fundamental idea. Now let's look at that fundamental idea with an example. So a single card is drawn from a deck of 52 cards, right? So let's look at two events. We've got event A is just going to be that the selected card is a face card. And event B is the selected card is a black card. Now, if you think about our options here, you could pick a face card or a not face card, right? You could pick a black card or a red card. Now, event A is this. Event B is this. So, ultimately, we have 52 total options. There are 26 black, 26 red. There are also 12 face cards and 40 not face cards. Now, if you go even deeper, there's 6 face cards that are black, 6 face cards that are red. There are 20 face cards that are not face cards that are black, 20 that are red. There's our options. Now, let's find some probabilities. Find the probability, because we want to know if these two are independent or not. That's ultimately what we're looking for. So let's find the probability of B occurring. The probability that the selected card is black. We know that there's 26 out of the 52. So it's 26 out of 52, which is 1/2 or 0.5. Now, if these are truly independent, the probability of B given A should also be the same. So the probability of B given A would be the probability of B and A happening at the same time over the probability of A. And we can figure those out. The probability of B and A, so black card and face card, that's 6 out of just the face card is 12. So that would be 6 out of 12, which happens to be 1/2. They are the same. Because it's 1/2, we know it's going to be the same for like anything else. Probability of B given not A would still be the same. So because these are the same, we can say that events A and B are independent. The probabilities do not change based on something else occurring. Okay? So let's look at another example. Let's say A and B are independent events. Can we find the probability of A or B if the probability of A is 0.35 and probability of B is 0.15? Now let's think about our formula. The probability of A or B, sorry, I just wrote that wrong, would be the probability of A plus the probability of B minus the overlap. Now we know in this case the probability of A is 0.35 and the probability of B is 0.15. But this is not the same as saying mutually exclusive events. This is independent. So we know they're independent, so we can find that last piece. So the probability of A and B is multiplying. We know they're independent, so we can just do 0.35 times 0.15. Okay, so the probability of B is not changed because A already occurs. So that does get us, I don't remember what it is, but let's just throw this down here. And so we're going to subtract whatever 0.35 times 0.15 is. I have this value ends up being 0.4475, or 0.448 is what you could round it to. That's important to know. It is important to know that these two are independent. If we didn't, we couldn't find this. There would be not enough information to actually find that last part, that and. Okay? Now, just because they're independent events doesn't mean we get rid of that last part. It's not the same as mutually exclusive. It's actually the opposite. Okay? So let's think about this. What do we know if A and B are mutually exclusive? So let's look at this situation. A single die is tossed. If they're mutually exclusive, we know that if one thing occurs, the other one can't occur. And that's the same thing. If you roll a die, only one thing can happen. So, like A occurring results is odd, B occurring, they're both, the probabilities are going to be 1/2. But they're mutually exclusive. So if I want to find the probability of B given A, okay, the probability of B and A divided by the probability of A is going to be 0 over 3. There are 3 odd results, but none of them are both odd and even at the same time. We can't get that. That's just not possible, which means this is 0. So even though the probability of B was 1/2, the probability of B given A is 0. 1/2 is not equal to 0. So these are not independent. So, a little theory here so that we actually know here. Um, Mutually exclusive, also known as disjoint, as there's no overlap, are not they are always dependent. They're not independent. So if two events are mutually exclusive, they are dependent. Okay. If one happens, the other one can't. That's just naturally the case. Knowing that one occurs means the other one cannot occur. So they are definitely dependent. So don't get independent and mutually exclusive mixed up. Okay. All right. Let's get into the second part of this lesson now. We said determining independence, now also probability of at least one thing occurring. At least once. So here's my situation. Let's say we toss 3 coins. I want to know the probability of at least one tails. Okay? Now, there are different ways to do this. You could make yourself a T-chart. Sorry, not a T-chart, a tree diagram, and show all these different possibilities. Okay? Because the first one is heads or tails. After that, depending on what you got, it's still heads or tails. I've just got a tree diagram of all the combinations, and now I'm going to write all the combinations. Could be heads, 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 tails, all the way down to tails, tails, tails. We have 8 different combos. 8's not bad, but sometimes there's going to be way more than that. So the probability of at least one tails is 7 of them. So 7 out of the 8. Now, I maybe didn't want to do all that. There's other ways. I want you to think about the fact that this is 7/8, everything else is only 1/8. So the probability of no tails is only 1/8. So sometimes, actually most of the time, it's easier just to find that everything else. Which is why I'm going to give you this formula. The probability of at least one of something. It's usually easier to find the probability 1 minus the probability of none or no of those things. So the probability of at least one tails, everything else is no tails. So if I can just find the probability that there's going to be no tails and then subtract it from 1, that's my answer. This is what I would use. Because if you think about it, they have to add up to the total. So we're going to utilize that by looking at 2 examples here. So Hawes currently has 7 cats and 12 dogs available for adoption. What is the probability that among the next 5 adoptions, at least one cat finds its home? So we could take all of those chances and adding them all up, or we can use the formula we just said. So the probability of at least one cat. Maybe it will be a little bit easier doing it 1 minus the probability of no cats. Right? So the probability of not getting a cat in the next 5, well, let's see. There's 12 dogs and 7 cats. That's 19 total. So out of 19, this first one, what's my chance of getting not a cat? Well, that's 12 dogs, so 12 out of 19. But I'm doing 5 of these, so it actually makes a little bit more work. 11 out of 18 would be my chance of getting another dog. 10 out of 17. 9 out of 16. And 8 out of 15. That's the chance of getting a dog each of the next 5. If I subtract all those from 1, when you multiply them up, you get 0.9319. So there's a 93% chance that that happens. You can add context. But if I did it the other way, I'd have to do the chance of getting a cat in one of them. So makes it a little bit more work in the next 5, but let's do another one. Don't take my word for it. Let's do another one. Among the next 3 adoptions, at least one dog finds a forever home. Let's find that probability. Okay. Again, same idea. probability of at least one dog would be 1 minus no dogs. So what did I have? 7 cats. So 7 out of the 19, that's my chance of getting a cat. Another cat would be 6 out of 18 because it changes when I get one. 5 out of 17. That gets me a probability of 0.9639. Again, that's a 96.39% chance I'm getting at least one dog in the next 3. All right? Let's look at a second example. Did you know that it's known that 23% of teenage drivers receive a moving violation? That's just some sort of speeding violation or like that non-parking violation within the first year of having their license, which means 77% don't. So among 4 randomly selected drivers, at least find the probability that at least one received a moving violation within the first year of having their license. Okay, we're going to pick 4 random drivers. We want to know out of those 4, at least one, because it could be 1. We'd have to find the probability of exactly 1. Then find the probability of exactly 2. Then find the probability of exactly 3. Then find the probability of exactly 4. Each of those might take a lot of work, and then we have to add them all up. So instead, we can do the probability of at least one ticket would be the same as 1 minus none of them getting a ticket. So, I know the probability of not getting a ticket is 0.77, so that is 0.77 times itself. We'll say 4 times, and I can get my probability. Now, by the way, this probability theoretically would change slightly because you're taking one person out, but it's such a huge population. With large populations, we're going to assume that they're independent, okay? Because it's not going to affect, even if it affects it, it wouldn't enough to change anything. So that actually, let me erase that and get the answer is 0.6485. 64.85% chance that at least one of them gets a ticket. One more with that. Find the probability that among 6 randomly selected drivers, at least one did not receive a moving ticket within the first year. Okay, wording like this can throw people off. So again, we're trying to find the probability of at least one not getting a ticket. Which means we'd be doing 1 minus the probability of no one not getting tickets. So that makes you think a little bit. Probability of no one getting a ticket was 0.77. So the probability of no one not getting tickets is all of them getting a ticket. So that's 0.23. That means yes ticket. Double negative there. So it's 0.23 to the 6th power, which it gives us a 0.999% chance. It's almost certain. And if it keeps going on like that, we can put this little plus symbol here to show that it's just going to keep going. It's almost certain that at least one did not get a ticket. All right, we're going to leave it at that for today. Again, today the goal is 2 things: to look for determining if 2 events are independent or not. So we did talk about these key things. If they're truly independent, then the probability of A should be the same as the probability of A given B, or not given not B. Those should all be the same. The probability of A should not change given other things. We can also use the formula. The probability of A and B should equal the probability of A times the probability of B. If we can find all those things and see if they're equal, we could state that. And the second part was the probability of at least 1. And that's where we can do the 1 minus. That's section 5.3c. We'll see you next time.